So good afternoon, everyone, and welcome to the Dogger Bank Wind Farm Report launch event that has been commissioned by Imperial Business Partners and Imperial Consultants with the Dogger Bank Consortium. We are thrilled to have you here and discuss the complexities and innovations in offshore wind project developments. So it's my pleasure to introduce the speakers, but before I do that, I just want to begin with some housekeeping points. So I hope it's not the case, but in case we hear the alarm, we just take the corridor and there's the stairs on your right. So just to let you know, there are toilets on that corridor as well in case you need them. The session is being recorded in case your colleagues or you want to share, in case someone didn't make it. So you will receive an email with a link and you'll be able to share that. You will be able to download the paper as well from the Imperial Business Partners page, which we will circulate via email after the event. And we will have a Q&A session after the panel discussion. So please keep your questions for that moment, and please make sure to speak up. Even though this is a small room, we want to make it available for the people online so that everyone can hear nice and clear. And with that, I would like to introduce our keynote speaker, Professor Peter Charles, and just provide a brief bio. Professor Peter Charles is a fellow of the Royal Academy of Engineering. He's a professorial lead in design engineer at Imperial and professor at large in the innovation design engineering at Imperial College London and the Royal College of Art. He was the founding head of the Dyson School of Design Engineering at Imperial.
Thank you ever so much, Lisa. We want to hear about Dogger Bank.
I missed the most important part. You were co-director of the Energy Futures Lab.
Okay.
So I just wanted to reach that part.
Thank you very much.
Peter.
Okay, so we really are here to celebrate the Dogger Bank innovation. And I have a few things to say. 10 minutes, and Louise will keep me to 9 minutes now. Innovation is everywhere, but innovation is the realization of value from creativity. And that's what Dogger Bank is all about, the realization of value to the wider society. But I have a few things to show you about innovation in general. So this is a robot on a blade. The blade has been stopped, sort of. But these blades never stop moving, and I'll show you that in a moment. So this is the blade bug technology using ultrasonics for scanning subsurface. Often looking for subsurface faults and flaws, and that's what's going on there. More of that in a moment. But I really wanted to show you this little video. I said blades never stop moving. So this is blade testing. So even if you stop it in a quiescent environment, you may well have 2 to 6 meters movement, and you get the idea from this. Okay, so the accolades, the world's biggest. You can only be #1 for a while. Somebody will come along soon and do something even bigger, or you'll extend it, which I really look forward to. But this is just superb news, and we will celebrate this. But it's not come easily. It's been a consortium of many companies and supply chains contributing towards this endeavor. And it is a good endeavor. What I love is benign interventions, benign impact. And this is quite rare in society. But I believe this is an example where within months you are surpassing the resource required to put into it and providing that net benefit to society. And it is large in scale. And we will hear more of that in the report and from other presenters. So we've heard all this. Oh, if you are going to be photographed with famous people, wear a green shirt. That's the only thing. So that was 10, 11 years ago, launching Dyson School of Design Engineering, producing the change makers of tomorrow here at Imperial, along with all of the other departments. But I wanted to show you where things like that get to over an 11-year period. So going between launch of one person is now a community of practice of 1,000 people. But one of the teams emerging from our nascent school and your nascent project, that's the connection, is the Polaron company applying AI large scale for doing sustainable batteries, doing the anodic cathodic structure in such a way that you've got self-healing materials. So you can do those 500 recharges with next to no degradation in performance for your batteries. So I look forward to 10 years' time with Dogger Bank. In terms of what I do, it extends from the nano. This is a temperature sensor for injecting into cells, living cells, to the macro, these large scale interventions. I got old school. I haven't done an EV for 20 years, but I've done lots of cars, but now working on large scale hydrogen planes. Products for the self, diverse, but working on the city of the future. Dogger Bank, it is about providing that clean energy. I would love the UK to be a net exporter of clean energy. So wherever we're up to now, 50%, changes every day, look up the numbers, it's not enough. Until we're at 115, 130%, we've got a job still to do. I hope the companies in the room are pleased to hear that, because our society within the UK, within Europe, needs a lot of energy to do the things we want to do. Have any of us stopped flying? Oh no. So we need methodologies to produce large quantities of SAFs and maybe clean hydrogen for doing our super jumbos and feeding our habits. We run the Energy Futures Lab here at Imperial, part of the School of Sustainability, and we look at fuels, energy infrastructure, cities, policy and innovation, materials and sustainable power. And we do it at scale. There are about 600 of us involved, and this just gives you an indication of some of the materials innovations, extremely diverse, contributing towards endeavours like Dogger Bank. One of our professors has been influential on the pilings for offshore wind turbines, which are used worldwide as an example. And here at Imperial, we have hundreds of labs. So we do the theory, but we also do the practice. But we respect you in the audience as industry, because you take practice to the next level. One of the members sitting in the audience here today is Sylvain Lezay, and he does optimizations which are fast enough for real-time influence upon orientations of your turbines. And here you can see a greedy algorithm versus a cooperative algorithm. And of course, cooperative is better for getting your turbines to work together. Of course, this is large-scale computations. Sylvain's buying a large quantity of digits at the moment, to speed up his computations by 1,000 times. It's an exciting area. At some stage, you'll have some challenges with the inspection, repair, and maintenance. But of course, we have these visions of the quasi-autonomous ecosystem for inspection, repair, and maintenance. And already remote service vessels are moving between the personed to the unpersoned. I showed an image from the Dogger Bank build earlier, but this is the Enercon climbing crane, taking advantage of the platform and tower for construction. We use your energy. All of us use your energy, much of it for thermal comfort, whether you're too hot or too cold. So do not forget the importance of energy efficiency as embodied in the Qbot company doing thermal insulation for homes. This is Bladebug again. Here you can see an indication of subsurface absence of materials, 2 scans showing that it's repeatable. And then my last slide, I hope I'm not. I chose to finish with a slide on design thinking. And you will have heard the phrase, you do it because you innovate. And much of innovation is about an energy, get something going. Somebody somewhere came up with the idea of Dogger Bank at scale and then persuaded others to engage, and they persuaded others. So that energy to kickstart a program is so important. Of course, you then go through the innovation cycle of exploration, experimentation, always with empathy for your stakeholders. But that's not enough. You've then got to effect change, and we can see the outcome of that. You've got to do the details, design embodiment. But what is the purpose of all this? Ultimately, in the case of a business, it's to exploit all of that work for ongoing commercial benign benefit, so that you're into the win-win scenario, win-win-win scenario. Win for the companies, win for society, win for stakeholders and customers. Ladies and gentlemen, let's celebrate Dogger Bank today.
Thank you very much, Peter, for your remarks. I'm sure that the topics will keep coming and be bringing discussions as we go along. Next, I would like to introduce our authors of the report. This report, as I mentioned, was commissioned by the Imperial Business Partners and Imperial Consultants, and the title is Dogger Bank Wind Farm, an evaluation of changes, challenges, lessons, and opportunities from the UK's first HVDC offshore wind farm. So our speaker is Kaylen Camacho McCluskey. She's a research assistant at the Energy Futures Lab, she recently graduated from a master's in environmental technology at Imperial College London, where her dissertation explored health as a policy driver for energy efficient renovations in owner-occupied households. And she was led by Dr. Aidan Rhodes, who's a research fellow based at Imperial College at the Energy Futures Lab as well. He's currently Energy Policy Briefing Papers Fellow, working on preparing a range of accessible briefing papers on topics of relevance to energy sector, policymakers, and stakeholders, as you know. Take it away. Yeah.
All right. Hi, everyone. Welcome to this presentation on our latest case study report, all about Dogger Bank Wind Farm, and particularly about the journey of developing and executing the HVDC transmission system. So in this presentation, I'm going to start by providing a brief overview of Dogger Bank Wind Farm for anyone who's not aware of the project. I'll then talk a little bit about HVDC technology for offshore wind, and then I'll look more at the project itself and discuss some of the success factors and some of the challenges, and then go on to discuss some of the recommendations. Oh, and here, I've included an image that shows a kind of bird's eye view of Dogger Bank, which is actually made up of 3 projects called Dogger Bank A, B, and C. And Dogger Bank A and B connect, this is the northeast of England, but it's not too clear, but they connect to Creaky Beck, and then Dogger Bank C is connected to Teesside, also in the northeast. So about Dogger Bank Wind Farm, as has already been said, once complete, Dogger Bank Wind Farm will be the largest offshore wind farm in the world and generate 3.6 gigawatts of offshore wind energy, which is enough to power the equivalent of 6 million homes in the UK annually. It's also the first offshore wind farm in the UK to use a high voltage direct current, or HVDC, transmission system to transmit energy from the offshore farm to the onshore grid. And the project is a joint venture between SSE Renewables, Equinor, and Vårgrønn. And Hitachi Energy is the primary contractor for the HVDC converter system. And the findings from this report that I'll be presenting today come from a mixture of desk-based research, but also primarily interviews with stakeholders from SSE Renewables, Equinor, and Hitachi Energy. And on the right here, I've got a brief timeline of some of the kind of progress from the project to date that highlights, firstly, I think the longevity of the project and executing a project of this scale, and also some other key milestones, like when they first achieved, when first power was achieved in 2023 in Dogger Bank A. So I thought I'd provide firstly an illustration of the HVDC system at Dogger Bank Wind Farm. Again, for anyone who doesn't know what that would look like. So essentially, the main components are the wind turbine, then an offshore converter station, an onshore converter station, which then connects the main AC network. And each phase of the Dogger Bank project operates with a 320 kilovolt HVDC transmission system. And one of the major innovations of this project is the offshore converter station, which represents a really significant leap in power capacity to 1.2 gigawatts per station compared to previous models, which I think were closer to 900 megawatts. And the team were actually also able to create a design that is comparatively really lean, and that saw a 70% reduction in the size of the topside, making it also more environmentally friendly. And then to talk a little bit about HVDC technology more generally and why it is that Dogger Bank chose to opt for an HVDC transmission system. So the first thing is the fact that this is a project of an enormous scale, and each of the sites A, B and C are located between 130 and 190 kilometres from shore. And there's essentially a break-even distance after which HVDC becomes more cost-effective than HVAC, and that's around 70 to 90 kilometres. So for scale and distance reasons, HVDC was the optimal choice. But also HVDC supplies additional benefits over HVAC. So for example, there are lower losses, there's a smaller right of way, and there are additional grid support and ancillary services like active and reactive power control, black start capabilities, and there's another one. And it can also help to protect the offshore grid and offshore wind farm and onshore grid from transients. HVDC is also expected to play a growing role in enabling more complex and integrated wind farm configurations, like multi-terminal and multi-infeed offshore wind farms. And then now I'm going to talk a little bit about some of the success factors. Again, most of these are drawn from some interviews that I had with stakeholders from SSE, Equinor and Hitachi. And through these conversations, we were able to distill or kind of pick out some key factors that contributed to the success of the project. I'm going to touch on all of them, but I'll focus a bit more on this first one because it's quite unique to Dogger Bank and was proved to be a really effective strategy. And that was the fact that they adopted a three-phase strategy with a standardized HVDC design. And that three-phase strategy refers to the the decision to deliver Dogger Bank as A, B, and C in this staggered way, which meant that they could then design or opt for an HVDC design and copy paste it across those three phases. And essentially, this provided a lot of value in terms of cost savings and just overall efficiency. And some of the specific things that were noted during interviews was the fact that, firstly, using this standardized approach meant that the team could then increase their buying power in the market because they were presenting something that was more long-term and scalable. And so that drove down costs for consumers. There was also the opportunity to overlap study and construction phases across projects. So, for example, knowing that the site conditions would be the same for Dogger Bank A and Dogger Bank B, they were able to. Sorry, one moment, I've lost my. Sorry. Yeah, so sorry. Knowing the site conditions would be the same for Dogger Bank A and Dogger Bank B, they were able to carry out studies like pre-engineering studies for both phases at the same time. And then lastly, they were also able to improve efficiency and quality or see significant improvements from project to project. So the amount of fixes that they needed from one stage to the next significantly went down. One interview even said that it was roughly a 60% reduction in punches. So they're like snags or small fixes, as I said, that appear during construction. An additional advantage of standardisation that appeared in literature, but are also supported by experiences from Dogger Bank, about that standardisation can help to streamline production, reduce cost of installations, increase quality, enable economies of scale, and increase compatibility with future markets. So as far as the additional success factors, one of the other ones was the way that the HVDC system was collectively designed. So one interviewee called this a collaborative design alignment process. So there was already a base design, but then there was this process of the companies coming together to collaboratively refine and create a much more detailed study that would meet the key objectives for Dogger Bank, like the 1.2 gigawatt power transfer target, or compliance with the grid codes. And some of the characteristics of this collaborative design alignment process included really focusing on delivering fundamental design features. So rather than just thinking about what was nice to have, thinking more about how they could really create a functional design, maintaining open, transparent communication, and then also building on each team's respective areas of expertise. There was a real kind of flexibility to the collaboration. Then there was also a focus on early risk mitigation and minimising the need for later interventions. So given the scale and novelty of the project, a lot of preparation went into the initial planning, and there was a focus on a safe by design approach to ensure that risks were addressed proactively, because there are more risks when you're working with that sort of distance. And then finally, and this is something that runs through some of the other success factors, is this commitment to maintaining a collaborative working culture or working approach. And some of the key factors that supported this long-term collaboration were, as I said before, a commitment to open communication, a shared sense of ownership over the project, and the fact that people work together as one team. They also built on pre-existing relationships from previous projects, and they also signed a preferred supplier agreement ahead of time. So yeah, these strategies helped address challenges as and when they arose. This isn't a comprehensive list of challenges, but I've just taken a couple of them to show some of the different sorts of things that arose when Dogger Bank was being executed. So on the development side of things, it took quite a long time to get the development consent order, almost 4 years, which is partly due to the nascent state of the industry, but also because of how time-consuming the consenting process is for a project of this scale. I highlight this because it's something that is still ongoing, and there are still issues with how long development consent orders take, even for projects now, where there is more time pressure, given our 2030 ambitions. Then there were also a number of macroeconomic and geopolitical challenges. So, for example, related to the COVID-19 pandemic, which made it much more difficult, for instance, to check the quality of components when they couldn't actually go in and see them, so they had to do everything remotely. Then issues related to the war in Ukraine, which led to a surge in the cost of steel. And then, broadly speaking, the global energy transition, which is creating a supply chain squeeze for HVDC components. And then there were also a number of local and on-site challenges, again, related to the distance, because teams were sent out for 2 weeks at a time, which made communication more complex, and also increased the risk or the cost of errors. And there were also factors to do with the unique weather conditions in the Dogger Bank zone, challenges related to procuring the specialised vessels needed to install the HVDC system components, challenges related to procurement of labour and skills, and also coordination with third-party developers. And this last one is less of a challenge. It's more about the fact that, well, I suppose in itself it is a challenge. Like, for example, Dogger Bank C was built right next to RWE's Sophia wind farm onshore converter site, as they had to navigate a relationship with what in theory is a competing developer, but they found ways to collaborate and actually ended up collaborating on certain elements of project execution, like they did stakeholder engagement together, because it's more effective for the local communities if companies come together to discuss what it is that they're building in those areas. And then on to the recommendations. So again, based on these success factors, and based on the challenges, we're thinking about how we can leverage or use experiences from Dogger Bank to create an offshore wind industry or sector that is primed to meet our net zero ambitions, and that has greater adoption of HVDC technology, strong, stable domestic HVDC supply chains, resilient networks, and long-term collaborative business partnerships. So I've put the abridged version of the policies that go into a lot more depth into the report. But here on the side, I'll go through some of them. So one of the first ones is to introduce a maximum permitting time for offshore wind projects. The Global Wind Energy Council recommend mandating a 3-year permitting time. It was also then recommended to involve statutory consultees earlier in the project approval process so that developers can be made aware of potential roadblocks earlier in the application, in the approval process. And then based on the fact that the UK has now developed this expertise and skills in HVDC, there's reason to increase domestic investment in R&D related to HVDC to continue building on that, and especially where that concerns potential ancillary services. Then also increasing grid capacity to support integration of offshore renewable energy sources. So the government is already doing some of this work, trying to develop a more proactive network planning framework, but additional recommended measures include carrying out regular assessments of transmission network capacity needed to support offshore wind developments, also making sure that grid upgrades happening in tandem with offshore wind developments, and considering compatibilities with emerging technologies like energy storage. And then supporting growth of and stability of domestic HVDC supply chains through a more standardised approach. This is something that also carries over into the recommendations for offshore wind industry, the recommendation to standardise HVDC system designs across multiple projects, as in the case of Dogger Bank Wind Farm. Again, developing standardised grid interaction study methods, adopting a collaborative design alignment process with suppliers and other involved parties, prioritising longer-term collaborative business partnerships, and increasing information and knowledge sharing between third parties, like developers working separately on the same zones or sites. And I think, yeah, experiences from Dogger Bank highlight the fact that it's both productive and possible for competing developers to cooperate without necessarily foregoing the advantages of competition. Thank you for bearing with me.
Great, so thank you, Kaylen. We're now going to move on to our panel. So we've got 5 panel members, and if they'd like to come up and join us here. Right, okay, so I'm going to introduce you, not necessarily in order, but in the order of your bios here. So firstly, we have Alan Borland. He's a project director at SSE Renewables. He's had 50 years of experience in delivering wind farm construction projects. The last 6 years being responsible for the technical execution of the Dogger Bank project as senior project manager and turbine project director. Secondly, we got Lila Vasquez-Villamor. She's a chartered engineer, 6 years of experience in the renewable energy industry, primarily in offshore wind development. She currently leads the high voltage direct currents transmission team at the Dogger Bank offshore wind farm with Equinor. Thirdly, we have Rob McCarry. He is regional sales manager for the Hitachi Energy HVDC business in Northern Europe. He leads a team supporting clients and partners in the development of HVDC projects across the region, including large-scale offshore wind transmission connections. Fourthly, we have Dr. Mirabel Mules. She's an associate professor of economics here at the Imperial College Business School. She's the director of our new School of Sustainability and also the co-director for the Hitachi Imperial Centre for Decarbonisation and Natural Climate Solutions. And last but not least, of course, we have Professor James Gilbert. He is a professor of engineering at the University of Hull. In 30 years of research, he's tackled a wide range of challenges with the common theme of measuring, modelling and controlling engineering systems. So thank you all. Got a wide range of panellists from a large amount of disciplines who can hopefully answer your questions. But firstly, I'd like to start with just a brief introduction, a few minutes from each panellist, basically explaining what their thoughts are on the report and sort of where the discussion should go from here. So I'll start with you, and we'll carry on up there.
Thank you. So good afternoon, everyone. I'm Lila Vázquez, as Aidan said, and I lead the HVDC transmission team at the Dogger Bank offshore wind farm. And as you also mentioned, I work with Equinor, and I have been in the energy industry for the last almost 7 years now, primarily in offshore wind development. And the majority of that has actually been as part of the Dogger Bank project team. So very happy to be here today showcasing our project, and in particular with the lens of the UK's first connecting via HVDC. It's been a longer journey from early engineering challenges through commissioning and then a later handover of our first 2 phases to our operations team. And that has come with many lessons that I think Kaylen and Aidan have captured in a really good way in the report. I think it's clear that the offshore wind and HVDC technology will be key, not only for us to achieve our targets in terms of our clean power by 2030, but also to contribute to the security and the reliability of our power system. And in that regard, and with that context, I think 2 of the items that you mentioned, Kaylen, with regards to your industry recommendations are very, very important, and that's standardization and collaboration. And on the standardization part, my personal view is that it's not only the standardization of system design to enable that scalability, which is very, very important, as I'm sure that Grant will highlight, but it's the studies aspect, which is often underestimated, but it's really, really important, in particular, as we are looking to integrate more and more of this converter connected generation into the system. So yeah, looking forward to the discussion today.
Thank you. There you go.
Good afternoon, everybody. Grant Mackay from Hitachi Energy. And I joined Hitachi Energy back in 2005, working within the transmission space and working within what was the formative renewables industry in the UK at that time. So I've had the good fortune to be able to follow the development of the use of HVDC technology in a more mainstream way within the UK transmission system, but also seen the development of offshore wind farms from relatively small direct connected wind farms into the distribution network up into the larger scale AC connected wind farms, and now the Dogger Bank wind farm, the first large scale offshore wind farm in the UK being connected by HVDC. And I think first and foremost, the report that Kaylen and the team have produced is really a tremendous success story. When you look at the gestation time, the period the project took to develop from the original Crown Estate lease back in 2010 to the signing of execution contracts in 2019, and now, as Kaylen mentioned, 2023, first power for the first of those 3 transmission systems. It's a tremendous journey that the developers have gone on to actually, and the perseverance they've shown to get to the stage of moving into construction, and then the speed at which the project has developed, given some of the challenges that it's faced, COVID-19 being an obvious one, but far from the only one. I think it's a tremendous testament to the efforts of the teams who've been involved on all sides to deliver that. And I think one of the really key themes that comes through for me, alongside the clear benefits that we can see from the efficiency through the level of harmonisation and standardisation, is just the partnership and collaborative working. We achieve much more together when we work in a collaborative way rather than more traditional combative way that the construction industry generally has been more used to. So I think it's a really good, let's say, reference for developers and stakeholders looking at projects in the future. How can we take a slightly different path and bring that, let's say, additional efficiency and speed and scale of action that we all know we need if we're going to hit the various clean power targets that we have as a nation. Thank you.
Thank you. Alan?
My name is Alan Borland. I am a turbine director for the Dogger Bank project, but previously, as was mentioned, I've spent 6 years as senior project manager, responsible for execution, for construction, for design of Dogger Bank wind farm as a whole. I've been in the renewable industry for 15 years now. I started in onshore project construction projects a long time ago. Drier feet and more hair at that time. But over the past 15 years, I've been lucky enough to be involved in some of the biggest projects that SSE Renewables has developed and built. I get the difficult point now of just rehashing what Grant and Leila have said about the quality of the report, but I think what it has highlighted and being able to capture in a really succinct way the challenges that we faced, and large scale execution projects are never easy, but the opportunities that have been born from it and we've learned from Dogger Bank in terms of the collaboration at an early stage, and it's a message that we talked about numerous times, but from the very outset we look to have a one team approach to delivering Dogger Bank, to getting consistency, to continually learning from mistakes, whether those are on A and we learn from them on B and then on C. But it's the way that you can deliver at scale. Make no mistake, Dogger Bank is a huge endeavour. 3.6 gigawatts of clean green energy delivered over numerous years, and we need to learn those lessons. We need to carry them forward because we've got a big challenge and opportunity ahead. With the targets to 2030, with another 35 gig of offshore wind expected to be delivered. So learning lessons from that gives us the best advantage and best opportunity.
Thank you. Yes.
Afternoon, everyone. Lovely to be here to talk to you today. I was really interested in this project because there are several touch points with my own background that linked me into this. So in 2010, when this was first conceived, I was teaching power electronics to undergraduate students. And at that time, 1 kilowatt, 10 kilowatts was high power. So now to be seeing, HVDC systems that are a million times bigger is quite amazing that it's reached that level. Another connection is the Great Beck converter station. It's just down the road from me. I pass it every day on my way to work. And again, the scale of that is just immense. I think this report's really, really useful. I think it, in a sense, I hate to use the word, but it's kind of a microcosm. I'm not sure what a very big microcosm is, but it's a very big microcosm of the whole of the offshore wind industry as it's maturing, going from a project by project basis to a pipeline of projects. And in the project by project days, everything was designed new every time, and now learning lessons from one or a pipeline of projects is really valuable. I think one of the challenges to that is if you do everything the same every time, then you stifle innovation. And so getting that balance between innovation and standardization is really important. I guess the other really important lesson about partnership and collaboration, and in the offshore wind sector, we talk a lot about collaboration, and it isn't always quite as easy as it might seem. One of my roles at the University of Hull is leading the AURA collaboration, which is Hull, Sheffield and Durham universities, and then a wide range of developers, OEMs and so on. And what really got that collaboration going was a project, the Prosperity Partnership, that involved the three universities, Siemens and Ørsted. And because we were working on things, we had to do things together, and that really built the foundation. And now that's led on to Centre for Doctoral Training, where we have about 130 PhD students working in offshore wind, including kind of electrical systems aspects. So collaboration is difficult, but the prize is really valuable when you do get it right.
Brilliant, thank you. And last, Mirabel.
You might wonder why an economist with no background in engineering is sitting in front of you, but hopefully I can bring a few angles to the way we're reading the report. So thank you, first of all, because it was a report I managed to read without being an expert at all, and it shows the quality. I think, you know, as an economist and social scientist, there are great aspects to learn from Dogger Bank and the report, in that what we've realized here is something that is going to have to be scaled up globally to huge levels if we want to achieve the decarbonization we're all hoping for. And so understanding not only the engineering and the R&D challenges, but also the policy and the adoption and the progress learnings from this experience are you know, very valuable. In particular, I think also in terms of you know, we can't shy away from the problems of trade policy and how the bottlenecks that certain design and certain sourcing of the supply chain behind Dogger Bank might lead to, and how to build in resilience into what we're designing and creating. And so I think, you know, this is an example of where really the policy design of being at the crossroads of climate or industrial policy, but also R&D policy would be crucial to ensure that in the future, the UK and other geographies make sure that they create the right research priorities that are based on, you know, thinking of what are the spillovers that, for example, R&D and HVDC might bring to the rest of the economy, and how those types of innovations can also help more general productivity of the economy and progress and transition to net zero. So I think those questions and thinking about skills upgrading, etc., that are needed, as you mentioned, are key elements to keep in mind.
Brilliant. So thanks to all our panelists for those introductions and those things. So I'm going to start the question and then open the floor. So please think about questions you'd like to ask our panelists or indeed Kaylen. So the first one is really about, we talked a lot about the HVDC system here and how much bigger it is. So what is the key sort of advantages to the resilience, reliability we've seen in this HVDC rollout as compared to earlier designs? Would anyone like to start?
I can give it a go. At least at the start, and then you guys can chip in. In terms of HVDC in general, and perhaps focusing it on the technology that we have in Dogger Bank, which is a voltage source converter, but we've not gone the step ahead of that grid forming capability onshore. So I think it's worth making that distinction. If we're talking about the benefits that HVDC can bring in terms of the network stability and reliability, there's perhaps two items to highlight. One of them is improved dynamic performance, because we're talking about power electronics and a very fast control system. The HVDC system can react very quickly to disturbances or to faults in the network. And we have two other things that support that, which Kaylen has mentioned. One of them is the fact that active power and reactive power are controlled independently from each other. And then the other one is that the offshore wind farm is decoupled from onshore, essentially. So you are, whenever there's a disturbance and a fault in the system, you are essentially shielding the wind farm from seeing that, which improves the ability of the wind farm to reduce the stresses and to be able to ride through the fault. And at the same time, you have the onshore converter, which is injecting reactive power to support the network to recover from that disturbance or fault in the system. So that would be number one, that improved dynamic performance. And the second one to highlight would be the support to voltage stability as well. And that comes also from this ability to control reactive power and active power independently. That means that the converter, regardless of what active power generation you have on the wind farm, can support the network in whatever the network needs in terms of reactive power injection or absorption to support the voltage. And that's very important. And that's actually something that an AC connected wind farm doesn't have, or actually our synchronous conventional generators. So those two, I think, would be the main ones. And then based on those two, the fact that HVDC does allow you to connect to weaker networks because of this capability, which is something that would be quite challenging if you were just connecting an AC wind farm into a weak network condition, which is now more and more common in the UK.
Brilliant, pretty comprehensive answer. Would anyone like to add anything?
I could perhaps add a little bit more. Fully agree with everything that Liam said there, and I think it's true that the evolution of the voltage source converter technology is what has enabled the use of HVDC to connect large scale offshore wind in the way that it has. And I think one of the key steps forward that we see with the Dogger Bank projects was on one hand the performance and capabilities of the system, but it was also with the evolution of the power electronics within that system allowed us to focus hard on the energy density within the converter and also the loss levels within the converter, so that we could for the offshore converter look at something that was somewhat more compact than the previous evolutions of the technology, and that then allowed our partners able to develop the design of an offshore platform specific to that equipment, but focused on size and weight to really push A on the economic side, but B also to focus on ease of installation, given these are very large physical structures weighing thousands of tons, so there are very few heavy lift vessels offshore that can deal with that. So I think what we see with Dogger Bank is really a step forward, enabling a much wider use of the technology for applications such as this.
Brilliant. Any other comments? All very comprehensive. So let's open the questions to the floor. Would anyone like to ask our panel a question? Yes, please. Yes, in the pink shirt. Yeah, over there. You pick that.
So yeah, talking through earlier, the benefits of standardization make obviously perfect sense. But inevitably projects are different. Clients have their own particular interests or preferences, and engineers can't help themselves iterating and changing, etc. Sometimes for good reason. And then you've obviously got two developers within your consortium, very different portfolios. How likely do you think you'll be able to continue that standardization activity?
Take that. So there's a couple of points there. Our whole plan of developing as has helped us with standardization. I've been notorious in the past. I'm usually the one adding in something to the employer's requirements as an additional thing. And the nice to have. The approach we took from the start was reassessing what does a platform have to do. It needs to hold the HVDC converter technology. It needs to hold all of that electrical equipment that allows us to transmit back to shore. Everything else is then built around that. Platforms in the past have had helicopter areas, helicopter landing areas. Do you need? Well, actually, no. What does this platform need to do? So I think taking that approach, and that can be applied across all of the technologies that we use, is bottom up rather than looking what do you really need to have or any other asset to be able for it to do its job.
Anyone else like to come in?
Second. With what Alan's mentioned, I think it is possible. I think you're right where you have more than one party on the employer side. I think the first thing is there needs to be alignment of the goal you're heading for. And I think we saw strong alignment between the Equinor and the SSE teams through the development, that they were focused on function. Specific. I think that's the key when we talk about standardization of HVDC systems. What we're not talking about is a standard specification. For me, it's more about harmonization of functional requirements and stepping away from, let's say, specifying the grind, so that we're as has been mentioned, we're looking very much at what's essential to have, rather than what's nice or preferred to have. And really, it takes a strong team, on both sides of the table to achieve that. And as you say, engineers love engineering. They're not so fond of copy pasting. So it's making sure you've got the leadership and the clear message on either side to say, this is the target that we're aiming for. These are the system parameters that we have to work. How can we harmonise then? And I think we see across the there's a coalescing around a 320 kV symmetrical monopole configuration, as we see at the bank, and a 525 kV bipole configuration, as we see being built out by the likes of TenneT in Germany. So that we do have the start of that harmonisation. It's how do we get that down to then a manageable level that we can drive repeatability between projects, so we don't see the same configuration coming forward between different projects, but with a quite different set of more detailed requirements sitting underneath them. There will be differences, there will always be differences between projects. Getting that right balance so we can drive repeatability is going to be key going forward.
Brilliant. Yes.
Yeah, a couple of points. I think having two parties to the project is really important, because then there's an awful big challenge. So if one party wants to go off in a particular direction, they're really going to be able to justify that. Going back to the point about innovation versus kind of standardisation. If you can get to a situation where the parties have sufficient trust to share each other's roadmap where they want to get to, that really opens that ability to look at, not, yes, this is one project, so what can be next down the line? Get a better balance between that innovation, standardisation.
Brilliant. Any other comments? Great, thanks. Two more questions. So let's start on the end here, and then we'll move next.
Yeah. Hi, I'm Vikas Pal. I work here. So, talking about this stability, you said we are going with this voltage source converter, grid following mode, not forming mode. I have understood correctly, or it is providing stability. So my point is that we have 3.6 gigawatt coming in, and then 2 converter stations on the land are converting it to the AC. So in this country, we have maximum 400 kV transmission system. So we need, each of them has a natural loading of 400 megawatt to 500 megawatt. So we need at any point of time, if we have full production, 8 to 9 400 kV transmission systems always ready to evacuate the power. So in your whole design, how the transmission side has been planned or expansion planning has been included. I need to understand that. Unless that happens, we have this lesson of sea green that we cannot accept the 1 gigawatt itself. Now it is 1030 watt. We cannot accept because we pay every hour 155,000 pounds as a constant cost. So this is costing the customers 1 million every year. or cuttling the wind. So how have we learned from those mistakes to build it to the success of this project? I want to understand.
Let me start again. From at least, I guess there's two aspects there. There's the aspect of how our wind farms interact with the wider network, and the aspect of the constraints, right? Which is the thermal constraints are I understand the aspects that are then leading to curtailment in certain scenarios of wind farms like Seagreen. That's not something that as a developer we have full visibility of. When we do our grid connection process with National Grid, we get a firm offer, right? And we are guaranteed that we're going to be able to export our power in all circumstances, unless there's an outage on certain circuits. So as far as we are aware, Dogger Bank doesn't have any constraints in terms of our ability to export power, but obviously we don't have the knowledge that NGET, the National Grid Electricity Transmission, have, or the National Energy System Operator, NESO, of how they need to operate the network and how they can best arrange the power flows from the wind farms.
Yeah, I mean,
yeah.
Thermal constant is what? I'm talking about the stability constant. You mentioned about voltage stability. So surge impedance loading is 400 megawatt for 400 kV. If you don't load beyond 400 megawatt, you have a flat voltage profile. If you load it, even more than that, you have a voltage drop. So we need at any point of time 9 sort of 400 kV circuits always under operations. Otherwise, we'll not be able to evacuate 3.3 gigawatt when the wind is blowing in its full value. So this should not lead to, in 5 to 10 years time, again, some kind of the additional constant cost to the customers. I am quite actually, disappointed with this, the constant cost, and we are paying 52 pence every night as a connection cost, right? So this is by far the highest in the world. So it's essentially such a big project of 3.6 gigawatt had to have a massive transmission system expansion planning altogether. Otherwise, it's again going to be, constant cost, and we have to pay again CFD. The CFDs are already arranged, so you have to pay two cost. The contract for different cost, and then again the curtailment cost. So only time will say. 5 to 10 years time, we'll be able to know whether it is a success or not.
There's a couple of it. I mean, quite happy to take it offline if you want, but I think what the gentleman has expressed there is maybe a conflation of technical and commercial issues, and I think I'll talk to you about it afterwards if you like. But I think to say that you're paying double is incorrect and misleading. You don't pay double for your curtailment fees as well as your CFD price.
So could you just introduce yourself?
Hi, Aidan. Sorry, it's quite a motive thing. I'm like, you get loads of electrical engineers in a room together, you go, sparks will fly, literally, or hopefully not. Hi, I'm Aidan Rhodes, head of supply chain at Renewable UK. You might have seen my name on the slides. But I was also very privileged and proud to have worked on the projects as well with some great colleagues from today. So that's who I am.
Thank you. Yes. Would you like to finish off and then we'll move to Noga?
Yeah, I'll be very quick just to give you additional comfort on what we have been doing in Dogger Bank. We obviously have very extensive grid code compliance studies, and as we go through our phases A, B, and C, we are including all of the generation coming from the other phases. So we are doing our studies with the 3.6 gigawatts of export into the network. And a key part of what we are studying is how the connection of our export systems affects and interacts with the wider network, both with synchronous generators and with non-synchronous generators, wind farms, facts, batteries, all of those kind of things. That's a key part of our grid code compliance process and studies that we carry out to a very large extent of detail. And those are the ones that I was mentioning to Kaylen, because they are becoming more. So we are studying all of that to make sure that there's no adverse interaction with the rest of the network.
Thanks.
I just wanted to add, not on the technical side, because I leave that to you, but on the commercial side, I think in parallel to the R&D and progress that's being made, the engineering and generation side, there's also a lot of innovation and thinking into market design and also into demand response and how, you know, that can be embedded in understanding better the incentives of customers, of commercial units, and being more responsive, and therefore integrating these types of new sources in a more flexible way. You know, we can't isolate the two.
Yes, absolutely. Brilliant. Let's have our next question. Yes, the gentleman.
Hi, senior engineer BPP. So recently I saw an article about RWE complaining about Dogger Bank's wake effects impeding their generation value. So when it comes to collaboration, then there's these barriers that are being built because RWE aren't going to be happy now supporting Dogger Bank. So how do you see this as a barrier, and how do you foresee overcoming this barrier? Would it be through government regulation policy, or do you believe the industry itself will be able to collaborate and address this issue and can work together to stop each other from knocking each other down, essentially?
I will in a minute hand over to Renewable UK. But I guess from a project perspective, what we have demonstrated, and of course there has been a lot of press about ongoing development and consenting for Dogger Bank South, but talking about just Dogger Bank and the construction we are doing, what we took the opportunity to do. What were originally Teesside A and Teesside B, which were now Dogger Bank C and Sophia Wind Farm, are jointly consented projects, although the split ownership, which happened in 2017. So it was massive advantages to working together. And that included doing shared works along the cable route to minimise disruption, you know, really improving our relationship with stakeholders. But there was a cost benefit as well. So I do think you can see that there's obvious benefits to collaboration. They have to be taken, certainly when you've got an ambitious programme of delivering wind farms. They're going to be explored. We've seen examples of that throughout. Of course, there's going to be a commercial discussion. I'm not going to even near that, but I think once you see the benefits of collaboration, that can actually mean amongst developers and share an idea is passing on improvements that can be made. And we'll get the industry. At that point, I'll pass to you.
I can't really add anything. I've not really looked at this topic in great detail, and it's something that I wouldn't want to answer, given that it's a deeply complex and commercial issue. So I won't add anything other than to just recognise the point that is one consideration that to think about on a national scale, given you look at the prospective amount of deployment that to achieve in regards to 2030, as well as a net zero system, which is approximately 117 gigawatts of offshore wind. So we've got to figure this out, and I'm sure we will do. But we also have to think about it in the context of how it sets precedents for the whole deployment for the UK.
James. Yeah, just going to make a couple of points. I think one of the aspects of this is that it came as a bit of a surprise. You know, the farm wakes would have an effect, but I don't think anyone really understood the extent. And even now, I don't think anyone really fully understands how significant an effect it is. There is, you know, as an academic would always say, there's a need for more research to really understand, you know, how significant those effects are.
Points on that. Brilliant. We have another question. Yes, please. At the back there.
Yeah. So
you can come next one.
Charles from Department of Civil Environmental Engineering. I'm very interested in the sustainability side of this project and the life cycle management of this wind farm. As far as I know, wind turbine maybe only have a lifetime of 20-25 years. So I was wondering, what is the design life of the wind farm? This is the first question. The second question is about the wind turbine blades. And I know it's very difficult to recycle. And I was wondering, do you have any solutions, like considering the end of life wind turbine blades by the like after 20 or 25 years? And the third question is about the UK's policy about the wind turbine blades, end of life wind turbine blades. Are we going to stop landfilling the blades in the UK, or are we going to stop exporting those waste blades to other countries? Do you have any comments? So that's my question. Thank you.
Yeah, two answers. I mean, yes, there are solutions now. So, you know, for the Siemens factory in Hull are now making blades from recyclable resins for the Sophia farm that they're being installed as we speak. But obviously, that's 25 years down the line before those are at the point of decommissioning. And there's still questions about, yes, you can recycle the materials, but what residual strengths do they have? You know, what applications can they be used in? Obviously, in the meantime, there's a lot of turbine blades out there that need processing. There are solutions, but none of them currently are great. But it is an area of research. I think it's unrealistic to think we'll take a turbine blade, recycle it into a new turbine blade. There are lots of other uses that we can make for it, some better than others. And again, there's a lot of research going on to try and find those most cost-effective and environmentally sound approaches.
Any points?
Yeah, I'll just raise one other point on it, and you summarised blade position. But if we look at just at design life, so certifiable design life for structures is typically 25 years under all of the codes and standards. But we are pushing it. It's a big thing that Dogger Bank. How do you monitor the wind farm? How do you monitor loadings? How do you monitor condition to extend that lifetime to operate for as long as you can before you need the decommission? So we've put in place lots of new technologies instead of in terms of structural health monitoring to allow us to do that and to operate for as long as possible.
Brilliant. Thank you. Okay, go on. I think you had a question.
Yes. To mention, we've done a few years ago some work with the European Commission regarding the integration of offshore wind. And one of the core aspects was that there was a big difference between connecting individual offshore wind farms versus building offshore network. And I was just wondering to what extent now these showcase of Dogger Bank is this, and this HVDC and so forth, is this the agenda in terms of how we're going to do, because, you know, the plan is to have more than 400 gigawatts offshore wind. And to have this I just wanted to ask you, is that on your agenda, and what's the approach?
The larger offshore networks.
I can maybe start the ball rolling on that one. That I think it's a very good point. I think if you look at the volume of wind the volume of wind that's planned, say, across the North Sea, so not just in the UK but around the northern parts of Europe, it's very clear that there are benefits, not just in terms of minimising of infrastructure, but there's some benefits you can get from resilience if you increase the level of interconnectivity. Today, I think it's fair to say that the technology is largely there. We don't see big technology gaps in moving to a more interconnected HVDC system. Yes, once you go beyond a single protection zone, you need HVDC breakers. And to date, there's been no industrial project has come forward that requires one. But from a Hitachi Energy point of view, we have a design ready for one project that has a real world application for it. And I think worth to note that the TSOs in Germany have now awarded, I think, 2 different innovation projects, one of those to ourselves, looking at the build out of a multi-terminal DC system based on an onshore hub, which will be built out in stages and will at some point then include HVDC breakthrough. So to me, it's a solid industrial project taking the first step towards exactly what you say. I think we've got some very good, holistic design thinking within the UK, within the system operator, and looking at what a more coordinated network might look like for the UK. And I think as we go forward, the next discussion will be, well, how does that go from a holistic level design into a more detailed design, and how can the regulation and policy follow that facilitates it coming forward into practical and deliverable industrial projects. And I think if I can't talk for the different stakeholders in the industry, but the way the regulation stands at the moment, I think it's very difficult for a generation developer to take forward the sort of anticipatory investment or co-development and investment that's needed to make a business case for systems like this to fly. So there's definitely a role for the transmission owners, for example, in that. But what that looks like, I think, is a question probably to put to the regulators and the policymakers as to how they see the industry being able to take that next step.
Yeah, as I got to mention, there was about 50 billion euro savings. We have a strategic, for this every individual wind farm being connected. And also linking the interconnectors with wind was also significant benefits. But I agree with you, that's policy and the current approach is not there at all. Yeah.
I think we will get there, but I think the question is what's the horizon until we do. And there's no doubt these networks are more complex. They're more complex to design and more complex to operate. So we need, say, the codes and standards and principles for how to do that on a larger scale.
Anyone else like to come in? Lots of questions? Okay. We'll start with you, Louise. Have you got a question from online?
Someone online's asked, what do panelists think will be any negative impacts of potential hostile attacks on the HVDC infrastructure, like cyber attacks or cable damage?
So, and cyber attack and cable damage. Any comments? Anything you're allowed to say?
I guess a wind farm of size becomes critical national infrastructure and attack. Clear rules and requirements for cyber security that we take very seriously and obviously addressed. I'm afraid the question on actual physical attacks. So certainly no add-ons to the boats out there.
Well, yeah, I mean, like I know tagging so on has been a big topic recently. Yes, outside the scope of the maneuver, I think. Any other comments on that one?
Yeah, question.
Brilliant. Yes, we had another.
Sorry.
Oh, yes,
It is being looked at, just so people are aware and are some sort of confidence. So I think the question was quite valid in terms of recognizing the two differences in cybersecurity perspective. And I'm on the project. I've never seen so much time and energy dedicated to understanding how cybersecurity on critical assets. I looked at a lot of good work was done. Also, from a physical perspective, I'm not just exaggerating here. We obviously appreciate the risk that's associated with subsea infrastructure, but from an energy perspective, pipelines, telecoms, as well as power cables as well. So a number of those things are being looked at a sort of MOD level and across the industry as well.
Brilliant, thank you. Okay, yeah, we had another question over there. So yes, go for it.
Hi, I'm a second year mech-eng student here. My question was about, would you say the innovation in the actual turbine and wind farm design has sort of plateaued? We sort of made it almost as efficient as we can. And if so, is future development going to be in the structure of these farms and the conversion technology that is focused on so much with Dogger Bank?
I've got the answer. has it plateaued? I think what we've seen is a bit of consistency over the past developing turbines 18, 21, 24 megawatts. So I think it will still continue to grow, but it has grown at such a huge rate. When I started, my first turbine first turbine I built was 2.3 megawatt Siemens machine, 93 meter rotor. So doubled that now in terms of rotor diameter. However many times in terms of megawatt capacity. I think the important thing though with turbines is not just that there has been this continued arms race, bigger, bigger, bigger. It's how do you build a truly sustainable industry around that as well? You have the ability not just to make turbines bigger, but make them better. So longer term, how do you make more consistency? How do you get secure supply chains and well-established supply chains? That comes against the arms race. So I would like to see a plateau because we're running out of vessels that can actually install these offshore that are big enough that continues to grow. But I think there's going to be a continued evolution as well.
If I can add, I imagine, not being an expert, but that the innovation can come on many other aspects of the turbine. For example, I was in Japan visiting Hitachi, and there, the innovation that's needed is how you make it float. So you can't have it only bigger. You have to have it floating and secure against other risks. So I think, if you look at the solar industry, and people kept thinking it would reach some level, and the innovation continues.
Yeah, I think you can say that innovation has not progressed, as plateaued. I think in terms of, in one sense, it has. We are only seeing 3 blade contracts turbines. And yes, they're getting bigger, but there's lots of innovation within that. So yeah, my own area is blade manufacturing. That's changed hugely from the materials used and the quality, productivity in the manufacture. And I think one of the key drivers for that going forward will be the industrial growth plan for offshore wind, which is really about ensuring the UK supply chain can contribute. And obviously, the UK has got a lot of great innovation that it can offer to ensure that
Okay, would you like to also?
Yeah, do you mind if I just give a few reflections? So again, I think one of this project has got innovation all over it, and I know we're focusing on the transmission aspect because to reiterate the point, the first time UK's had a DC connected offshore wind farm. That's a real big milestone. I think from recognizing the cost aspect, I don't think anyone on the panel has yet mentioned what the CFD price was for Dogger Bank as well, which was the lowest price for an offshore wind farm that's ever been realized. And when that announcement was made, I think it was again another sort of line in the sand of how offshore wind is so significant in terms of cost. Obviously, there's an indexation. Was it 39 or 37? Can someone help me out? Whatever it was, but I mean, there's indexation to be put on that. But obviously, the cost of electricity and the cost of power is very much in the news at the moment. But bear in mind, those prices were established before COVID happened as well, and obviously the invasion of Ukraine. So, real big project with regards to helping to reduce the cost of energy. I wondered if I could put Leah on the spot. Another great piece of innovation, or at least some of the challenges, connect to the fact that when you are using the onshore, Still, yeah.
Okay.
The offshore convert station is being used to provide grid stability services. I wondered if you could speak to that a lot. And perhaps some of the challenges that we had with the interface or the integration of the turbine. Yeah, the report actually.
So on the first one, with regards to the services that we are providing to the network, that's for Dogger Bank C that connects to Lackenby substation. And because of a nuclear generation that was going to be phased out around that area, National Grid developed this P9's Pathfinder, in which they were looking for new plants that would be able to provide reactive power services. So we essentially raised our hands at the time and said, we have a fantastic converter here that can provide the reactive power that you need. So that's essentially the service that we're providing to the grid, and is one of the items that I was mentioning earlier with regards to being able to support voltage stability in the area in whatever way the network needs it. So yeah, the last thing we need there is the final connection to the national grid. But as soon as it's ready, then we'll be very much there supporting the network. And your second question was with regards to the integration.
Yeah, just that there are challenges when you're building a first-in-class transmission system and using new turbine supply, and how perhaps there were challenges and how project with all the stakeholders were able to overcome.
Yeah, it's we're getting into electrical engineering territory, which is fun. But yeah, one of the challenges that we had was the integration of our large HVDC converter, which is controlling voltage and frequency offshore in the little network that we have created for the wind farm, and the converters on the wind turbines themselves. When you have power electronics, there's always a risk that they interact adversely. So these were studies that took actually several years of very hardcore engineering and having detailed models from both sides of the converter, putting them together and assessing lots of different scenarios of what can happen actually in the offshore network and in the onshore network, and how do we make sure that we are interacting in the correct way. That was new. That was new for us. It was new for Hitachi, and it was new for General Electric. And it's another example of a really good one-team approach and collaboration.
Does seem like the one-team collaboration is almost the key innovation story here. So I got one more question. We'll time for one more question.
Just on that point, I work in power system stability, so I'm a bit tempted to ask when you talk about voltage stability. So you say that in that area, all the nuclear plant and complex would be replaced. So we are replacing plenty of synchronous generations. So the synchronous generations are being now replaced by this 3.6 gigawatt of in-feed HVDC. So naturally, and then also you mentioned that you are working on a grid following mode. So nuclear generators or any synchronous machines, they are voltage source. They always act as a voltage, source. Whereas this is, if it is a grid following, it's mainly a current source. So how is that voltage support or reactive power, dynamic reactive power support is going to be guaranteed? What was the rationale behind choosing, grid following mode? So that's what I wanted to learn from you.
Grid following converters at the time, I mean, Grant, you will know a little bit more on this than me for sure. But at the time, we explored the possibility of having a grid following converter also onshore, and the complexity was too high in terms of the risk that we were able to take as a developer, and also the cost was actually very high at the time.
So but then how do we guarantee the voltage support? Because you are claiming that you are providing voltage stability. So when the network is weak, naturally in grid following mode, it does not provide stability. That's all understood. So it only has to be on a grid forming mode so that it can provide voltage. A solid reactive power has to come. Like synchronous generator is an active reactive power source. Whereas if it is working as a current source, it does not provide the reactive power.
We do provide reactive power support, both absorption and injection to the full capability and rating of the converter.
No, you provide the reactive power, but that does not necessarily guarantee the stability because the network is weak.
No, we support it, but we don't act like a grid forming converter. You are absolutely right. The level of stability that a grid forming converter is much higher, what they're able to provide. So we are a level underneath, so to say, even though we still provide support to voltage stability.
Thank you.
Brilliant. Okay, well, I think it's now time for our reception. So thanks a lot to all our panelists.